Okay, today we will see about the inner orbital complex or outer orbital complex. When outer orbital d orbitals are used in bonding, the complex is called as a outer orbital complex. They are formed due to the weak ligands or high spin ligands, and hybridization is sp3d2 hybridization. They have octahedral shape. So if outer orbitals or outer d orbitals are used in bonding, then the complex is called as a outer orbital complex. And if outer orbital complex is there, then they will have weak field ligands or high spin ligands. So we can ask which type of ligand fields is there in the given complex. Clear? For that we need to see it which type of the orbital is used. As in this part we have already know that now if outer d orbital is used, then it is what we call as a weak field ligands, and these weak field ligands are also called as high spin ligands. If weak field or high spin ligands is there, then hybridization should be sp3d2 hybridization, and they always have octahedral shape. Clear? So this is what about the inner orbital complex. Now we'll see about the then outer orbital means that inner orbital complexes. Okay, so when d orbitals, that is one now n-1 cells is n-1 d sub cells is used for chemical bonding, then when d orbital of n-1 cells are used, they are known as a inner orbital complex. They are formed due to the strong bond field ligands, and this if strong field ligand is there, then we can say it as low spin ligands, and if low spin ligand is there, then hybridization should be d2 sp3 hybridization, and they also have one of octahedral shape. Now let us see first one, that is one of 6 ligands, that is unidentate, 6 unidentate ligands is there along with the complex and having one of octahedral entities. For that, let us see one examples. The inner orbital complex, one example of this is one of CO means cobalt, then NH3 6 times, then within the complex what we have 3 plus. Okay, so that means one of it is a cation. There. So what is the name of this complex? Hexa amino cobalt 3. Okay, so the now in this hexaamino cobalt 3 we need to understand the atomic number of this cobalt first, isn't it? So after that we need to write the electronic configuration of cobalt 3 plus by removing 3 electrons. Okay, so cobalt will have outermost electronic configuration 3d 7 and 4s 2 electronic configuration. Okay, and from that to remove 3 electrons, that is one of 4s2 we have removed, and one from one of 3d we have removed. Okay, so the remaining, that is one of 3 CO3 plus ions will have the electronic configuration 3d 6 and 4s 0. Clear? And then we have 4p is also blank. Clear? So here we need one of 3 NH3 molecules, sorry 6 NH3 molecules. So we need to make 6 space. Clear? Okay, so in order to make this 6 space, what we need? We need to rearrange the 3d electrons. Clear? When we rearrange the 3d electrons, means that from 3d you will get 2 empty orbitals by pairing 2 in the 3 orbitals. So along with this 2, 4s is there, and then 4p is there. 4p have 3 orbitals, 4s have 1 orbitals, 3d have now 2 empty orbitals, isn't it? So altogether we have now 6 orbitals, and these 6 orbitals will be used for chemical bonding now. Okay, by sharing with electrons from the ammonia. So the hybridization becomes what we have 2 from 3D, and 1 from 4s, and 3 from 4p. So D2sp3 hybridization. Okay, so this CO NH3 six molecules within the complex, then 3 plus ions will have, or now the electronic configuration together as here. The electronic configuration we have here is here in this 6 orbitals. Your ammonia, 2 electrons of ammonia will be sit here all together in this 6 orbitals. That is one now 4s, 4p, and your 3d. Clear? So like this we have this one. Like this one, ammonia will be here, ammonia will be here, ammonia will be here, and ammonia will be here, ammonia will be here, ammonia will be here. So now here we have know that on all the electronic in this electronic configuration, all the electrons are paired now, isn't it? So it become what? The magnetic wave properties will be one of dimagnetic in nature. So this is the part which is very important in this chapter. Okay, there. Like this one, let us see COF63 minus. So for CO we already know that 4s2 3d7. So now this here 3 minus means now you need to find out the coordination number. Coordination number means what is here? -1 for fluorine, -1 into 6. That means x plus -6 equal to -3. So x equal to +3. So 3 electrons will be lost here, isn't it? So after 3 electrons will be lost from what now? 2 electron from 4s, and now your 4p have 3 orbitals, and 1 from 3d orbitals will be lost. So 2 is from 4s2, or 1 is from 3d. Okay, now we need to have one now outer orbital complex, as I already told you. So you need to use now d orbitals from 4d, not in the 3d. Okay, so we need to rearrange the 3d molecules. Instead of that, we use now outer 4d orbitals. Okay, so if you use one orbital from 4s, and 3 orbital from 4p, and 2 orbital from 4d, then the hybridization become one now d2 p3s, means that now sp3 d2 hybridization. Okay, clear? So within this 6 empty orbitals, all the fluorine electron will donate electrons here and occupy here. Okay, so you have one now 4s become 2 electron for fluorine, and 4p become one now 6 electron from this fluorine, and this 4d have 4 electrons from fluorine. Okay, now altogether in this this compound COF63 minus, now the electronic arrangement become 3d6. Okay, and within the 4s 2 electrons from fluorine, and 4p 6 electrons from fluorine, and 4d will have 4 electrons from fluorine. Okay, so what we have here, all the molecules with all the electrons in 3d, now we have 4 ampere electrons, is not? 4 ampere means what we have? The magnetic properties become paramagnetic. Clear? So like this one, to find out the magnetic properties and your structures and hybridization is very important for the finite point of view. Okay, so like this, and we have 6, isn't it? 6 means what is the figure? Octahedral figure. And this is what about the octahedral figure. Now 4 ligands united in the tetrahedral structures. Tetrahedral means 4 ligands are there. So 4 ligands will be directed at the corner of the tetrahedral figure. So they will have tetrahedral structures. Now let us see what is the difference between inner orbital complex and outer orbital complex. You can record this one. Now, if inner orbital complex is there, then we have one strong field or low spin ligands. Okay, and in the outer orbital complex is there, that means outer d orbital is used, that we have weak field or high spin ligands. The hybridization is of dsp2 hybridization in case of tetrahedral entities. Okay, tetrahedral means 4 orbitals you require, is na? 4 means 1 from d, 1 from s, and 2 from p. So like this one. And hybridization is of sp3 hybridization in case of what? Outer orbital complex. In case of inner orbital complex, it is of hybridization is of dsp2, whereas in case of outer orbital complex, hybridization is of sp3 hybridization. And if inner orbital complex is there, it will have square planar shape, whereas if it is of outer orbital complex, then it will have tetrahedral shape. Now let us see about the inner orbital complex. One example, let us take it. NiCN4 2 minus. Okay, Cn have -1, so -1 into 4, -4. So x plus -4 equal to -2. So x become +2. So nickel have +2 oxidation state. Okay, so while writing the electronic configuration, outermost electronic configuration is of 3d8 4s2. Okay, so in order to get Ni2 plus, you need to lose 2 electrons. So 2 electron is removed from the 4s. Clear? So for Ni2, electronic configuration is of 3d8 4s0. Okay, and you need to join one now 4 Cn molecules. So you need to make 4 empty space. Okay, so in order to make 4 empty space, our 4p is still vacant, isn't it? From 4p you get 3 orbitals, and from 4s you get 1 orbitals. Okay, so altogether you have 4 orbitals is there. Clear? But it is a inner orbital complex, means that you need to use inner d orbitals. So inner d orbital means n minus 1 d orbitals. Okay, here n is 4, 4 minus 1 is what? 3. So you need to use 1 d orbitals in the hybridization. Clear? So in order to use that, you need to rearrange the electronic that means arrangement in 3d. That means 1 electron which is in the 5th 3d orbitals is shifted to the 4th 3d orbitals. Okay, now 1 become free now. Okay, so in the hybridization we have 1 from 3d and 1 from 4s and 3 from so 2 from 4p. So hybridization become dsp2 hybridization. Okay, so NiCN4 2 minus have dsp2 hybridization. In this, 1 from 3d and 1 from 4s and 2 from 4p, the electrons of Cn, then electron pair of Cn will be stay there. So here in the arrangement, what you got? In the last arrangement, we got all the electrons are pair, isn't it? So NiCN4 2 minus will have pair means dimagnetic. Okay, so like this you need to find out the magnetism. Again, for the outer orbital complex COCl4 minus, you can do it yourself and you can see the arrangement here. I will not explain, it is same like as. So here 3d3 plus means that 3 coordination number, so you have removed 1 from s 4s2 2 electrons you have removed. Now so we have 4 orbitals is there in the 4p. So 1 is from 4s. So all this, when the complex become formed, 1 from 4s and 3 from 4p will be used. So your hybridization is sp3 and all the chlorine occupy here in this S4s and the 4p orbitals. So now in the arrangement what we have, single electrons are there in 3D, is na? So it is a paramagnetic. Okay, and this was in the 2020 exam paper, CBSE. Now let us see about the limitations of your valence bond theory. Okay, so in the limitation, first there is some shortage. On the shortage, number one is it involves the number of assumptions. That means this theory, valence bond theory, involves the assumption part. Okay, and number two, it does not give quantitative interpretation of the magnetic data. That means how much magnetic power is there, that was not explained in the valence bond theory. Okay, in the third point, it does not explain the color exhibited by the coordination compound. Here in this valence bond theory, we never see about the colors, isn't it? So it does not explain about the color of the coordination compounds. In the fourth point, it does not give a quantitative interpretation of the thermodynamic or kinetic stabilities of the coordination compounds. Means that it does not explain about the stability of the complex compounds. Okay, in the fifth, it does not make exact prediction regarding the tetrahedral and square planar of 4 coordination complex. That means it does not explain properly about the shape. Clear? So shape means that only hybridization can explain, is it not? But one hybridization will have different shape. So which shape will be there cannot be explained through one of valence bond theory. Okay, and it does not distinguish about the weak and the strong ligands. Means that distinguish between weak and the strong ligand. Means that which ligand will be strong, which ligand will be weak, cannot be explained by this theory. Okay, in short we can say that this theory could not explain the quantization of the magnetic data. This theory could not explain the quantization of the magnetic data, existence of the inner orbital or outer orbital complex. Means that when it becomes inner, when it becomes outer, cannot be explained. Okay, and another one is change of magnetic moment. That means magnetic property changes cannot be explained with temperature. Okay, that means if temperature is there, the magnetic properties will be decreased, and why it is, it cannot be explained by this theory. Okay, again it does not explain why most of the coordination compound have colored, that cannot be explained by this theory. So these are the limitations of this theory.